In section 10.2, we're going to be looking at linear systems of differential equations. A first-order system of differential equations that can be written in the form where we have all of the first derivatives on the left and they all equal some function of t times the different y's on the right plus a forcing function is called a linear system because these are linear first-order differential equations. So we're looking at a system of linear first-order differential equations, so we call a linear system of differential equations. So theorem 10.2.1 says, if we suppose the coefficient matrix A and the forcing function f are continuous on some interval a to b, we can let t naught be an a to b and let k be an arbitrary constant n vector. So it's a vector of magnitude of n that is filled with just constants. It is the set of initial values, or initial conditions. Then the initial value problem, the vector y prime equals the matrix A of t times y plus the forcing function with y of t naught equaling the constant vector k has a unique solution on the interval a to b. A more in-depth look at the system is given here on this slide, where we have y prime equals the coefficient matrix A of t, y, plus f of t, where f is also a column matrix, or a column vector. We call A the coefficient matrix and f the forcing function. So f of t, whether it's in matrix form or it is a single function when we're looking at one single first-order linear differential equation, is always called our forcing function. So it's very similar to what we did when we had only one ODE at a time. So we'll say that A and F are continuous if their entries are continuous. If the forcing function f is equal to the 0 vector, then we say our system is homogeneous. Otherwise, it is non-homogeneous. We're only going to focus on homogeneous systems through section 10.6, and then we will step in with variation of parameters to look at non-homogeneous systems in section 10.7. An initial value problem consists of finding a solution that equals the given constant vector k at some point that's our initial point t naught. We write this initial value problem in the same way we had on the first page. Y prime equals the coefficient matrix A of t times our vector y plus our vector of forcing functions f, which is also a function of t, and we have our initial condition y of t naught is equal to the constant vector k. Let's take a look at an example problem. For our example problem 1a, we want to write the system y1 prime equals y1 plus 2y2 plus 2e to the 4t, and y2 prime equals 2y1 plus y2 plus e to the 4t in matrix form, and conclude from theorem 10.2.1 that every initial value problem has a unique solution on negative infinity to infinity. Well, what we need to do is we need to pull out our coefficient matrix A of t and our forcing functions vector f of t. So this is where we're going to look at the coefficients of our y's. That's going to be where our A of t comes from. So A of t is going to come from the coefficients of y. We also need to find those forcing functions, which would be over here. Those are our f of t. And then, of course, in the beginning, we have our y primes. So this is where we're going to find our y prime vector. So what we know then is we have y prime is going to equal our A of t, which is going to be 1, 2, 2, 1, times our y, which I'm also going to put in blue, And then we're going to add to it our forcing function f of t. And we could write it as 2e to the 4t and e to the 4t. But typically, we try to make it a little simpler by saying, well, they both have e to the 4t. Let's just make our matrix only have constants. So we'll have 2 and 1, and outside will be e to the 4t. It's also a much more succinct way to write this. So here, we would then have, if we wanted to write it as an initial value problem, we weren't given the initial values, but what we could say then, if we wanted to, is we could say that to this we could add in a requirement that says y of t naught is equal to some column matrix or column vector that has k1 and k2 in it. We don't know what they are. We would have to be given that. And how can we guarantee that we are given a unique solution from negative infinity to infinity? Well, this is where we look at our coefficients matrix A. So A of t has all constant entries. So that means A of t is continuous everywhere. So it's continuous on negative infinity to infinity. If I look at f of t has multiples of the function e to the 4t. So f of t is also continuous on negative infinity to infinity. So a reminder of what, if you need to see a visual of this, what an exponential looks like. E to the 4t is going to look like this. And it's going to be continuous for all x. For example problem 1b, we want to verify that the given equation for y here, where we have 1/5 times the column matrix 8, 7 times e to the 4t, plus c1 times the column matrix 1, 1, e to the 3t, plus c2 times the column matrix 1, negative 1, e to the negative t, is a solution for all values of the constants c1 and c2. In this case, we have a couple of options. The first one is we could differentiate. We could see then if that equals a times y plus f, or we can use that y prime equals ay plus f to multiply a by all of y and add f to it and see if we end up back with y prime. So let's see what happens. So let's look at, so if y prime equals ay plus f, then that would be a here, which was our 1, 2, 2, 1. And it's going to be times this entire solution, which is the 1/5, 8, 7 e to the 4t, plus c1, 1, 1, e to the 3t, plus c2, 1, negative 1, e to the negative t, plus our forcing function f, which was 2, 1, e to the 4t. So remember, matrix multiplication is a little different than scalar multiplication. But what we end up having here is we would have 1/5 times 1, 2, 2, 1 multiplied by 8, 7 e to the 4t plus c1, 1, 2, 2, 1 times 1, 1 e to the 3t plus c2, 1, 2, 2, 1 times 1, negative 1 e to the negative t, and we would add to it 2, 1, e to the 4t. And the reason why the A matrix is on the left in every one of these matrix multiplications is that remember that matrix multiplication requires us to keep things in the same order. If I have A on the left, it is always on the left. Left multiplication and right multiplication are different. So here we would have 1/5. Well, now we have a 2 by 2 by a 2 by 1. We'll end up with a 2 by 1. So if we do row 1 times column 1, we end up with 1 times 2 is 8, plus 2 times 7 is 14. 14 plus 8 is 22. And then when we look at row 2 times column 1, we get 8 times 2 is 16, plus 1 times 7 is 7. 16 plus 7 is 23. E to the 4t. And in the same way, we're going to multiply 1, 2, and 1, 1. So 1 by 1 is 1, plus 2 by 1 is 2. 1 plus 2 is 3. So we get 3, and then we'll also get a 3 when we do 2 times 1 plus 1 plus times 1. So C1 times the column vector 3, 3, e to the 3t, plus C2. 1 minus 2 gives me negative 1, and 2 minus 1 gives me positive 1, e to the t, plus 2, 1, e to the 4t. If we now combine the e to the 4t terms, we end up with 1/5, and we had 2 on our forcing function. But remember, it's taking a 5 out, so we're really going to have to add in 10 then to keep it the same. Oops, so we end up with 32. And then when we want to add 1, considering we're pulling out a 1/5, we're going to have to add 5, so it'll be 28. Total e to the 4t's plus C1, 3, 3, e to the 3t, plus C2, negative 1, 1, e to the t. So if I were to make one small adjustment here and made this instead minus C2 and 1, negative 1, oops, I forgot my negatives on those e to the t's, then we would see that this is really y prime. So let's look at our y and take y prime of the given y. Well, it would be 1/5 times 4 times 8, 7, plus C1 times 3 times 1, 1, plus C2, oops, I forgot the e to the 3t. Oh, and I think I forgot the e to the t's before. Let me make sure I don't forget my e to the t's. So the first one was e to the 4t, there we go, plus C1 times 3 times 1, 1, e to the 3t, plus C2 times negative 1, 1, negative 1, e to the negative t. So what do I really get? 1/5, 32, 28, e to the 4t, plus C1, 3, 3, e to the 3t, minus C2, 1, negative 1, e to the negative t. So we were able to verify that y is indeed a solution here. For the last example here, problem 1c, I ask you to find the solution of the initial value problem y prime equals 1, 2, 2, 1 y plus 2, 1 e to the 4t, so same setup, same problem, but now instead I give you an initial value for y where I've got y of 0 is 1/5 times 3 and 22. So in this case, what we need to remember is at times 0, when t is 0, y is equal to 1/5 times the column matrix 322. And also from part B, if you'll remember, y was given as 1/5 times the column matrix 8, 7, e to the 4t, plus C1 column matrix 1, 1, e to the 3t, plus C2 column matrix 1, negative 1, e to the negative t. So what we're going to do is we're going to evaluate that solution at 0. So where does that leave us? Well, we know that 1/5 times the column matrix 322 then equals 1/5 8, 7, column matrix 8, 7 times e to the 0 is 1. Okay, so that's done. Plus C1 times the matrix 1, 1, plus C2 times the matrix 1, negative 1. So what we can do from here is do a little bit of simplification. What we can do is subtract the 1/5, 8, 7 over to the other side. So we end up with 1/5 times, let's see, that would be negative 5, and 22 minus 7 would be 15. And it would equal, on the right-hand side, 1, 1, 1, negative 1 times C1, C2. Oops. There we go. So really what we have is we get negative 1, 3, equaling 1, 1, 1, negative 1, C1, C2. So here, all we need to do is an augmented matrix with Gaussian elimination. I'll grab a different color here. So we would have 1, 1, 1, negative 1, and our solution's negative 1, 3. Well, we already know that we could say negative 1 times R1 plus R2 is going to give us our new R2. And let's see where that gets us. 1, 1, negative 1. And then negative 1 plus 1 gives us 0. Negative 1 plus negative 1 gets us negative 2. Negative 1 times negative 1 is going to be a positive 1, plus 3 gets us 4. And then if from there, if we do negative 1/2 R2 is our new R2, we end up with 1, 1, negative 1, 0, 1, negative 2. So therefore we know that C2 is negative 2, and then C1 plus C2 equals negative 1, or C1 equals negative 1 plus 2, which is 1. So we can then state our solution to this initial value problem as y equaling 1/5, 8, 7, e to the 4t, plus C1, which is 1. So we'll just have 1, 1, e to the 3t, and then C2 is a negative 2, so we'll have minus 2, 1, negative 1, e to the negative t. And there is our solution. So let's take a look at what homework I gave you from this section. From this section, I only gave you problem 1B, 5B, and 8B, but check the posted homework set to see if I'm collecting all of them.